Hello class, we're on lesson number 5 in chapter 4. This is our last lesson for this chapter, and it's called More on Graphing Functions. Now before I begin, I just want to put a little disclaimer here. We're going to be reading something that you may not necessarily doctrinally believe. I personally don't, but I just want to clarify. We're just going to look at this in a sense from a standpoint of math. Okay, and we talk about the Earth being 15,000 years ago. Some of us adhere to a lesser time frame in which the Earth has been around, and we won't get into the long conversations regarding these things, regarding science. We do teach science from a Christian standpoint and from a creationist standpoint, and then when we get further and deeper into how long we believe the Earth has been in existence, we may not necessarily come to any agreement with 15,000 years, but let's again just approach this from a mathematical point of view, and let's take a look at what they're presenting mathematically and set aside anything that that we may not necessarily agree with or believe. Okay, so let's read. Geologists think that 15,000 years ago, the level of the Earth's ocean was more than 1,000 meters lower than it is today. If this is true, the shorelines of the continents have changed in appearance. The maps above show how the Atlantic coast of the United States is thought to have looked 15,000 years ago, and how it looks now, and how it may look in the future. So now we do know how the Earth changes, particularly the shorelines and how they're affected by the oceans, and so we can understand that there is a change, there's an effect over time, and I think that's really what we're looking at here. And again, approaching this from a mathematical point of view and setting the time frame that we have here. Let's take a look at what they're going to teach us regarding this function of time. Okay, now the levels of the ocean is a function of time. The graph below shows how scientists think that it has changed in the past. The x-axis represents time in thousands of years, so -40 represents 40,000 years ago, for example, and the y-axis represents the changes in level relative to its present level. -50 represents 50 meters below the present level, for example. So notice that, first off, we're not going to be using the actual value, say 40,000 on the graph. In fact, -40 and -50 are really two distinct units of measurement, and not only that, they're actually the true value of these things are represented different. So we have time, but that number -40 is really supposed to represent -40,000. So let's just take that approach. Now, in a sense, it does change the scale of our graph, but if we're consistent with that scale, we can still see the effects, or we can see how the graph changes over time. And we can see how the graph at -40 is right on the x-axis, and it starts dropping at -30. Then at -20, it's really taken a dip, and somewhere around -15, it's really low at its lowest. In fact, if you're measuring now, looking at the y-axis coming downward at let's say -30, it's approaching -50, and that would be the -50. That would be the meters below sea level. Okay, so we're talking about sea level, and at -20, it's surpassed -50. It's probably closer to about -60 or so. But when we see it get to about -15 in terms of time coming across the x-axis, at -15 it's at its lowest point, which is beyond -130. Okay, or excuse me, 100 itself. It's probably somewhere close to about 100 and maybe 110, 120. But now we're gonna now when we say sea level, I'm sorry, it's not a direct it's not a very direct relationship to sea level. In fact, they're just comparing it to the sea level at its present point. So if you were to mark a line in the sand where the sea level is today, so now we're saying from this point it's -50, -100, -150, -200, all the way down. That's what they're using that as we call a point of reference, and we've used that before. So it's not necessarily that it was, in terms of sea level and how we measure it today, we can only measure it from where it is standing today. It wouldn't make a whole lot of sense to change the sea level to a different point in time and then start measuring from there. We're measuring from where it is today. Now, we have also seen positive as much as we've seen negative. In fact, when we talk about going up mountains and we say how far we're above sea level, okay? And that's how we measure even the height of mountains. Mount Everest, which is somewhere about 29,000 feet above sea level. Okay, so we're using the point of reference of sea level. Okay, so let's go back to the top of 171. As we already know, the graphs of many functions like this one include negative numbers. One way in which to draw a graph of a function is by plotting points from a table. Now we're going to look at a different function. So we just kind of use this again to illustrate, show you a graph with negative values both in past, what regards time, and below sea level. So we're going negative and negative, and we find ourselves, if we were to expand that first graph out, we knew we would be in the third quadrant, because above it is the second quadrant, and diagonally it would be the first quadrant, and right next to the right of it would be the fourth quadrant. So we're in the third quadrant there. So if a formula for a function is known, it can be used to make such a table. In this lesson, we will make tables and draw the graphs of functions that include both positive and negative numbers. Here are examples to help you recall how it's done. Now, we have already used the negative values, and we have been graphing, and in fact, we did go into all of these quadrants at some point. But now we're using negative numbers or negative values for x and y. So obviously it's going to show us a line that extends beyond the first quadrant. It can go, in fact, you can easily cross 3 quadrants. This particular example 1, we can see it's actually in the second, the first, and the fourth quadrant. So it extends, and we can see positive and negative numbers on both the x and the y values. So draw a graph, and we're going to show example 1. Draw a graph of a function y is equal to 5 minus 2x, and let -2, -1, 0, 1, 2, 3, 4, and 5, or let x equal. Now, the solution, first we use the formula to find the y numbers. So we have to do our mathematical function, plugging in the values, -2 for x, and we're going to have y is equal to 5 minus 2 times parentheses, or -2. That's the x value of -2. We do our math, and we come up with 9. Then if x is equal to -1, again, we do our math, and we come up with 7. Now we can create this table. You've done this before. And we're going to put our values in as they told us, -2, -1, 0, 1, 2, 3, 4, 5. And in the y in the y area, we're going to see all these values that would have been the answers to our formula when we substituted the values for x. So we have our table, and now we plot the points. And we can see at over on our graph, the points seem to lie on a line. So we've connected them with 1, getting the graph shown to the right. So here, let's take a look. We have the -2 value. If we were to go across the x-axis, -2, and go all the way up to 9, +9, it would put us all the way up there at the very top left corner. And then we'd have -1, 7, and you can see 0 is 5, and we're going down all the way. Then at one point, our positive number for x turns into a negative y value, we have 3, -1, keep going down, 4, -3, and then 5, -5. So those last 3 points are below the x-axis, which means their y values are negative. Don't want to get it too confusing, x and y's, but just note that we went from positive or negative positive all the way to positive positive to positive negative, meaning the x and y values, which means we're crossing into the negative territory of the x, and then we'll come back into the the positive territory of x, going across, and then going up and down, we're in the positive territory, and we crossed into the negative. Once we cross that x-axis coming down, we're in negative y territory. Okay, so let's take a look at our next example. And what are they going to do? Well, they're just simply going to now use the rational number. Remember, we did use integers before. Now we're going to use rational numbers. Now with rational numbers, we're going to be very careful. We have to make sure that we create the proper units and for our graphs. So let's just take a look at first the formula, and we have draw a graph of the function y is equal to x squared. Let x vary in tenths from 0 to 1. So what do we have here? We have x and y. We have a table here, and we see the x value going from 0 to 0.1, that's 1/10, 0.2, that's 2/10, then 3/10, 4/10, 5/10, all the way to 9/10, and then 1, which is really 10/10. Okay, so 10/10, think about a pizza pie being cut into 10 slices. There are 10/10. Now, when you have one whole pizza. Now, we look at the values when we square the x value, and we notice that we're getting values that are in hundredths. So we have 0 is 0, but 0.1 is 0.01. And as we look down, we're squaring, but we're ending up with hundreds, 0.04, 0.09, and as we go all the way down until we get to 1 again. Why? Because 1 squared is 1. Now there's something peculiar about this, because we notice that these hundredth values increase fairly rapidly. Okay, if we were looking at the x value, we would notice they increment equally by 1/10. But we notice that's not necessarily happening with the y value. With the y value, we go from 0.01 to 0.04, and then 0.09, then 0.016, and then it immediately starts escalating very quickly. And it's not proportional the way that we were incrementing. It's not equal in that same proportion of increasing by 1/10 or anything. What increased from the first to the second was an even higher increase. In other words, we went from 0.01, and let's start writing on the board here. 0.01 increased to 0.04. So that was an increase of plus, sorry. Now, let me rewrite that. Now I'm just bringing this up because we should take note of this anytime we see numbers that change. So let's say drastically. We have 0.04, and the change here to 9 is now plus 0.05. So we're not increasing. The x value increased 1/10 in each case, but the y value increased at a different rate. And if we go down and we see now the change in the next one is 0.07, the difference between 0.9 and 0.16. Then it's 0.9. Then it really takes off. 0.11 is the difference, and then 0.13, and then it becomes 0.15, and it really jumps up. So this is telling you something, and we've already dealt with it, but you're going to recognize these things, that something is growing here exponentially. And when we say exponentially, it means that as you increase a number, the other is increasing at a greater rate. And we are seeing in our formula. an exponent. We have x squared. So this is just a little sneak peek into this particular function. If we turn the table or turn the page to the next to the graph, we will see a curved line. The graph is a curved line, and the reason it's curved is because it's not directly proportional. It's not a direct variation where one thing increases the other. When it increases at a certain point, the other one increases by a particular amount, and that those equal increments of x will always have equal increments in y. We're not seeing that here. We're seeing an equal increment of x being 1/10 is different from the increment in y at different points. So that's why we're getting this curved graph, okay? And we talked about inverse. Now we're talking exponential. The inverse you saw, remember it increased. I'm going to attempt to draw it here. It would curve downward and just make a nice little curve there. And I just ran out of room on my tablet, but let's just say it's curving in that manner, right? And we had our graph set up, and we knew that it would never touch here the y-axis, right? Because we discussed how the 0 would be affected in the denominator and how we can never approach, we can never attain a y. We won't go into that. We discussed it already. But now we're dealing with a different graph, and it's exponential growth. And it actually starts at 0, but it's growing and then it's curving outward. Now, I could just tell you that this is a nice graph to have if that's your financial portfolio, okay? It's growing and it's growing exponentially, okay? 1 year passed and it grew $1,000, but then another year it grew 10,000. You know, if you knew that it was going to grow 1,000 every year, it would probably just look like a straight line. But if it's growing at different rates, and obviously if it just continued to grow, and then because it grew even more every year, one of the reasons that may be, just giving you a practical application, is because whatever you made, you reinvested. That's the power of investments. It's also, negatively speaking, the power of debt and the power of misuse of credit. Okay, the reason I'm saying this is because these are two applications that you will learn in life. Debt, on the other hand, can increase also, if we're looking at this as something bad, how much you owe. And the reason why, let me just show you. The number that is being that is growing is also how much you owe, and then the percentage is being taken off of that. We'll explain that more in our classroom, but the point is that you'll see these curved graphs that grow either positively or negatively very quickly over time. They start growing quicker and higher, and the rate of change becomes so much greater. And so I wanted to focus on that in terms of graphing, particularly graphing functions. But these functions that we discuss with negative numbers can be linear. We have linear graphs. You are going to be given the opportunity to graph both, and both linear and the exponential, as I would call it, graphs. Inverse graphs, you know, when they change, are another type of graph. But let's just we'll focus on the fact that we can use negatives, negative values, which you have learned in other lessons, and also we're going to be entering into these rational numbers. And I want to make one more point regarding the graph. On page 172, if you notice, look at what we have. We have really just the number 1 being the value at the very top of the y-axis, and 1 the value on the x-axis. So but you can see that the graph was broken into tenths. And if you see the increments, of each of these lines were actually 1/10 going across till we get to 0.05, either going across or 0.05 going up. Now, what the person that graphed it had to sort of estimate where the hundredths would lie. So we had a 0.01. If you look at 0.01 was basically 0, it's the first point. We put 1, and 0.01 is just hugging the x-axis. We know it's not on the x-axis, it's moving upward. But then look at 0.02 is a 0.04, which is almost half of a tenth. Okay, so you can see it's almost halfway up. And remember, it's only going up by tenths. Now the third one is 0.09, and it's again hugging now below the 1/10 line. But as you can see, as these numbers begin to grow rapidly, they shoot up in a curve upward. And the point I want to illustrate here is that you could see we can graph using different units of measurement. We don't necessarily have to just say whole numbers, 1, 2, 3, 4. We can say all 10 of these actually represent 1, and we can break them up into tenths. We can really use anything. The only thing that I would recommend is you try to stay consistent. If you're doing it across, do it upward as well, the same way. Imagine what this graph would look like if we did these in tenths going across, and then we decide, you know, going upward, I'm just going to make these 1s, 2s, and 3s, and 4s. You can do that. In fact, that's kind of what they did in the other graph over here and on page 170. But unless your data sample is so distinct, you may not be able to notice the change. If we did that, we would actually have a small curve where 0 is, and it would just curve up to the very first line going across above the x-axis. But because we extended 1 to be all the way up at the very top and broke this into increments on the y-axis, it allows us to see that change. Particularly the change between one to another. If we would have just really squashed it all the way down and just go 1 here and do tenths going across, 1 going up, it would just be one slight curve that we could barely see. So we want to try to illustrate the rate of change. Remember, graphs help us to see that. And if we don't graph properly, I'm not saying necessarily by making errors, but saying by graphing in a way that we can't see it, the graph doesn't serve as much purpose. Okay, you want to be able to see it go up or go down or go up and down, obviously. And so that's another thing just to keep an eye on as you create your graphs. But we're not restricted to always have the same measurements. And again, I just refer back to page 170 where we see one line here was -50, but going across, 2 lines going across was -10. Nonetheless, we could still see the rate of change. We can see the graph serves its purpose. Certainly, you're not going to make 40,000 lines, so you have to shrink it somewhere, and the question is, where can you shrink it so that your graph makes some sense and people can see it? Imagine if you did it in a way that it just kind of looks like a line. You say, I don't really see rate of change. So they were able to make this graph to show the dip all the way down, and then it came back up. Okay, so that's just another thing to point out. All right, so move on now to our exercises.